Hey there, and welcome. I am absolutely thrilled to have you here for this explainer. Today, we're going to embark on a definitive, highly structured thematic journey, basically an A to Z cheat sheet, through the wild world of artificial intelligence. Look, if you've been feeling totally overwhelmed by the sheer volume of jargon out there, things like neural networks, embeddings, zero-shot learning, well, you are absolutely in the right place. Consider this your ultimate terminology toolkit, designed to demystify today's most complex technology in a way that's clear, focused, and actually makes logical sense. Let's get into it. To kick things off, let's look at this quote. It says, "Artificial intelligence means lots of things, depending on whether you're reading science fiction or selling a new app or doing academic research." And honestly, that hits the nail on the head, right? The term gets thrown around everywhere because even the top experts debate these definitions and the field is literally redefining itself daily. We desperately need a clear, structured framework to understand what this tech actually is, how it works, and where it's headed. Okay, let's dive into this. Our journey today is broken down into 4 quick chapters. Number 1, the foundations of AI. 2, mechanics under the hood. 3, bias, fakes, and complications. And finally, number 4, the future frontier. All right, chapter 1, the foundations of AI.
We are starting our alphabet journey with A for algorithm. Now, at its core, an algorithm is simply a sequence of rules that a computer uses to complete a task or make predictions. It is the fundamental building block underpinning the technology that makes our modern lives tick. Seriously, whether it's that smartphone app you literally just opened, the social media feed you scroll through, or the GPS guiding you to a new restaurant, algorithms are the invisible instructions making all those decisions happen behind the scenes.
Now, what's really interesting about this slide is the history behind the word itself. The term algorithm actually comes from this guy, Muhammad ibn Musa al-Khwarizmi. He was a 9th century Persian polymath who produced some vastly influential works in math, astronomy, and geography. His name was later Latinized as algorithmi, which eventually gave us the very word that defines our entire digital era. Pretty cool, right? Building on algorithms, we've got to clear up a very common mix-up. We need to contrast the broad umbrella of artificial intelligence with the specific tool of machine learning, giving us our letter M. You see, AI is the broad concept of simulating human abilities like reasoning, solving problems, or understanding language. Machine learning, on the other hand, that's a specific subset of AI. It's the study of algorithms that learn by finding patterns in sample data, which allows the machine to make predictions without being explicitly programmed for every single step. But you might be wondering, what do these machine learning algorithms actually learn from? Well, that brings us to B for big data. Over the past couple of decades, as computers got way more capable, we started collecting vast amounts of information about our lives and our planet. Big data is the field that deals with storing and analyzing these massive, complex data sets. And without big data to provide the raw material, those machine learning algorithms just wouldn't have the patterns they need to function. Wrapping up our foundations, we have C for chatbot. This is probably the most visible face of AI for a lot of us right now. A chatbot is just a software application designed to mimic human conversation through text or speech. We see them everywhere, from customer service bots to virtual therapists. They take those foundational algorithms, which are often powered today by large language models, process the data, and deliver it back to us in a format that feels incredibly natural. Moving right along, Section 2, Mechanics Under the Hood. So let's look at D for deep learning. Remember how we just said machine learning finds patterns? Well, deep learning takes that a massive step further. It's a highly advanced form of AI that uses neural networks to imitate how the human brain actually works. Instead of relying on a simple step-by-step algorithm to do a task, deep learning systems make predictions based on complex patterns they've learned previously. This lets them automatically extract features from huge amounts of data without us having to hold their hand. And how exactly does deep learning pull this off? Through our letter N, the neural network. This is the actual architectural structure making deep learning possible. Inspired directly by the biological brain, a neural network is made up of a large set of simple, interconnected computational units. It's this specific architecture that allows computers to do incredibly complex stuff, like recognizing images or understanding speech. Let's break down exactly how information travels through this network. It's a step-by-step process. First, you have nodes, which act as individual computational steps. These nodes are organized in hierarchical layers. So as data enters a node, a mathematical formula is applied to it. Finally, that processed output is passed right along to the next layer of nodes.
This repeats layer by layer, refining the information until the network spits out a final prediction.
And this brilliantly illustrates the concept. In this abstract representation, those simple colored circles act as the interconnected nodes, or neurons, in the system. Obviously, real-world models have billions of these things, but visually boiling it down like this really helps us grasp how data flows from one point to another, getting processed and transformed along the way. But wait, how does the network know which piece of data is the most important? That brings us to W for weights. Within those connections between the nodes we just looked at, there are numerical values called weights. Think of weights like fine-tuned dials. During the training process, the system is constantly adjusting these dials to determine the strength of the connection between specific neurons. It's absolutely crucial because it lets the model focus on contextually relevant inputs and just ignore the random noise.
We're going to conclude the mechanics section with E for embeddings. Okay, this one's a bit abstract, but it's super important. See, computers don't think in human words, they think in numbers. So to understand concepts, data is encoded into an array of numbers called a vector. Embeddings are specific vectors that map elements in relation to one another in a giant multi-dimensional space. Think of it like plotting words as coordinates on a 3D map. The distance between these vectors allows the computer to measure contextual relationships and actually, mathematically, understand meaning.
All right, section 3. Bias, fakes, and complications. A totally critical term we need to understand here is B for AI bias. AI bias happens when machine learning algorithms produce prejudiced results. It is so vital to remember that AI tools aren't just autonomous, neutral brains in a jar. They're socio-technical systems. That means they are designed, operated, and heavily influenced by the humans who build them and the historical data they're trained on. Managing these biased outputs is, for sure, one of the most serious complications we have to tackle in the field today. Moving to F for fakes, we encounter the deep fakes. The word itself is a mashup of deep learning and fake. These are synthetic images, audio, or video clips created by powerful generative AI networks. By utilizing those complex mechanics we talked about earlier, deepfakes can digitally alter a person so they look, sound, or act like someone else entirely. It creates highly deceiving content that, as you can imagine, raises massive concerns about misinformation. Look at the striking realism in these side-by-side variations. As discriminator networks, the parts of the AI trying to spot the fakes, get better at distinguishing real from fake, the generator networks get insanely good at creating synthetic media that is almost indistinguishable from reality. Seeing it visually like this underlines exactly why we have to be so aware of how this technology can be used. And finally, Section 4, the future frontier. We're going to revisit the letter A in our glossary, but this time for artificial general intelligence, or AGI. Right now, the AI we use is narrow. It plays a game of chess, or it generates a block of text. AGI represents a massive evolutionary leap. It describes a theoretical type of AI that can match or even surpass human cognitive capabilities across a wide range of tasks. It is basically the holy grail of AI research, aiming for a true, generalized, human-like intelligence. And honestly, we're already seeing steps toward deeper capabilities with Z, zero-shot learning. Traditionally, AI models needed to see thousands of examples of an object to recognize it. But zero-shot learning is a type of machine learning where a model can accurately classify data it has never even seen during its training. By leveraging semantic relationships and past knowledge, this accelerating AI can now predict novel, totally unseen concepts without direct supervised training. It's wild. Which brings us to the ultimate philosophical extreme, S, for the technological singularity. The singularity is a hypothetical point in the future where technological growth, driven by recursive, self-improving artificial intelligence, becomes completely uncontrollable and irreversible. The idea is if an AGI can build a smarter AGI, the resulting explosion in intelligence could lead to unfathomable changes for human civilization. And that leaves us with a final, provocative thought to end our explainer. The famous Turing test, proposed by Alan Turing, challenges a machine to exhibit behavior that's indistinguishable from a human. So here is the question. Will a machine simply pass the Turing test, mimicking us perfectly? Or will the accelerating pace of this technology mean we hit the uncontrollable technological singularity first? It's a fascinating timeline, and understanding these terms is your very first step in navigating whatever comes next. Thank you so much for learning with me today.